All right, so at the end of the last video, we started on this explanation of how a dot product is, in a sense, a measure of how close two vectors are to pointing in the same direction. So let's investigate that a bit. Remember, if you have two vectors that are pointing in the same direction, another way of saying that is that the angle between them is zero, whether 0 degrees or 0 radians. And so plugging 0 into that formula with the involving the dot product, we have u dot v equals the product of those magnitudes times the cosine of that 0 degree angle between them. But cosine of 0 degrees is 1, so this just comes out to the product of the magnitudes. Okay? This will always occur if two vectors are pointing in the same direction. The dot product of the two vectors is the same thing as the product of their magnitudes. And that's actually kind of an important application that we may use once or twice over the course of the semester. But let's look at some other facts here. So what if u and v are pointing in opposite directions? Well, you can think of them as the angle between those two vectors as being 180 degrees. They're pointing in opposite directions, so they make a straight line, right? That's the angle for a straight line. And in this case, u dot v would equal the product of the magnitudes times cosine of 180, which is equal to -1. And so we get the opposite of what we got up here, the negative product of those magnitudes. Okay? Now, if I let theta be any other angle between 0 and 180 degrees, and remember we showed earlier that the angle between any two vectors is always some number between 0 degrees and 180. Then what that means is the cosine of that angle is going to vary between -1 and +1. And so the dot product, which again we can evaluate this way, is always going to take on values somewhere between the product of their magnitudes and the negative of the product of those magnitudes. It can't be anywhere else. It has to take on values between them. Now, the closer this dot product here is to the product of the magnitudes of those vectors, the closer those two vectors are to pointing in the same direction. And the closer this quantity is, this dot product, is to this negative product of those magnitudes, the further the two vectors are away from pointing in the same direction. And again, remember, cosine of angles between 0 and 90 degrees will come out positive, not including 90 degrees, and cosine of any angle between 90 and 180 degrees will be a negative number. That's the second quadrant, not including 90 degrees again. And we already know that the dot product of two perpendicular angles, where the angle is 90 degrees, is 0. So basically what this argument shows is that if you have these two vectors and the angle between them is acute, you're going to get a positive dot product. And then if you take A, for example, and start rotating it away from B, that positive number is going to get smaller and smaller and smaller until we get to a 90-degree angle between those vectors. At that point, the dot product becomes 0. And then if you keep rotating A away from B, now the dot product becomes a negative number and is going to approach the negative product of their magnitudes. Okay, so that gives us sort of a little more meaning and intuition behind what the dot product is really telling us about two vectors. But there's more. There's much more to the dot product than even just that. So let's start looking at something that we call direction angles. Let's suppose A is a vector in R3. And a similar idea applies in R2 as well, but we're really mostly interested in R3 here. Let's also put place A as a position vector so that its initial point is at the origin. A forms angles with each coordinate axis, and we're going to call those angles alpha, beta, and gamma. Those are going to be the angles that correspond to the x, y, and z axes, respectively, between those axes and A. What I want to do is come up with some way of determining, if we know what the vector A looks like in component form, is there a way of determining all three of those angles? And we call those direction angles for the vector A. Well, we just got done talking about how the dot product relates to the angle between two vectors, and so there might be some way of working that concept into this problem. There is. So remember, the axes are not vectors. So if I'm going to try and use that dot product idea, I need to be able to take a dot product of a vector, A will be one of the vectors, with some other vector. And this is where the standard basis vectors become useful, because the standard basis vectors coincide with all three of my axes. So for example, if I wanted to find the angle between vector A and the x-axis, that would actually be the same thing as finding the angle between the vector A and the standard basis vector I, because I is on the x-axis. It'll have the same angle. So if we reframe the question that way, we suddenly have a starting point. So let's think of that in terms of the formula that we just came up with. If alpha is the angle that I'm looking for, the angle between A and the x-axis, I can use that formula to find the cosine of alpha. Cosine of alpha should equal the dot product of A with I over the product of the magnitudes of A and I. And then cosine of beta is similar. The I's become J's here. Cosine of gamma is also similar. We have K's in that case. Now, a couple of things worth noting here. Specifically, something interesting happens if you take a dot product of a vector with a standard basis vector. First of all, A, we're treating in a general way. We're saying that the components of A are A1, A2, and A3. But look at what happens when you dot it with the standard basis vector I. Because two of those components are 0, those are going to zero out these two components when we take the dot product. And then 1 times A1 is the only thing that's left. So if you dot a vector with the standard basis vector I, the result is just the first component of that vector. And you get a similar result if you dotted A with J or dotted A with K. For example, if I dotted A with K, then the result would be the third component of this vector. One way of actually thinking of that is that if you dot a vector with one of the standard basis vectors, then what you're actually looking at is a scalar projection of that vector onto whichever axis corresponds to that standard basis vector. You don't need to think of it that way right now, so if that's confusing, don't worry about it, but at least make sure you understand this right here. Now, not only that, all of the standard basis vectors are unit vectors, which is easy to verify. The magnitude of the magnitude of I, J, and K are all equal to 1. And that's useful because that magnitude shows up in each of these, or the magnitude of one of those standard basis vectors shows up in each of these little expressions up here. So how do things simplify? Well, looking at this first expression, we just showed that A dot I is equal to A1, the first component of A. Also, the magnitude of I is equal to 1, which means we can kind of get rid of it in this product. And this down here, my new denominator, is just the magnitude of A. So this is a simplification of this. And we can do similar simplifications for the other three cosines up here. Cosine of alpha is A1 over the magnitude of A. Cosine of beta is A2 over the magnitude of A. Cosine of gamma is A3 over the magnitude of A. Now, that alone is useful because we could pretty easily find all of those direction angles, but we're gonna show that these give us something kind of even more interesting in a moment. But before we do that, these quantities here, we call these the direction cosines of A. It's just the cosine of each direction angle. Those are called direction cosines. Now, if you were to take all three of these direction cosines, cosine of alpha, cosine of beta, cosine of gamma, and throw them into a vector so that they're the first, second, and third component respectively, then notice what happens using what we just did up here. Substitute A1 over magnitude of A, A2 over magnitude of A, A3 over magnitude of A into each one of these. And remember that the magnitude of A is a scalar. So I could sort of undo this step by pulling 1 over the magnitude of A out and treating that like scalar multiplication. So we end up with this vector containing our direction cosines being equal to this. But notice also, this vector A1, A2, A3, what's left here is just the vector A. And so what this is equal to is A over the magnitude of A, which is the same thing as the unit vector that has the same direction as A. We talked about that in 12.2. So what that shows us is that if you create a vector out of the direction cosines of a vector A, then that is identical to the unit vector that points in the same direction as A. That's pretty interesting if you think about it. So let's do a problem where we want to find those direction angles. Okay, so we want to find the direction angles of the vector 4, 4, negative 3. Okay, so cosine of alpha, cosine of beta, and cosine of gamma. Whoop. Okay, so alpha, beta, and gamma are what we are looking for, so we're going to end up taking an inverse cosine at one point. But based on the work that we did up there, cosine of alpha should equal the first component of this vector, 4, over the magnitude of this vector, which we're going to compute mentally. Remember, it's the square root of the sum of the squares of these numbers. 4 squared is 16, plus another 16 is 32, plus negative 3 squared would be 9, so 32 plus 9, that would be 41, making this the square root of 41. Notice beta is the same thing, 4 over root 41, and then we have negative 3 over root 41 right here. Okay? So, taking inverse cosines then, alpha is the inverse cosine of 4 over root 41, so inverse cosine of 4 over root 41. And if I were to plug that into a calculator and get a decimal approximation for that, I would get 51.34 degrees after rounding. Notice beta is going to be the same thing because it's the same value that I'm taking the inverse cosine of, 51.34 degrees. And then this one, we have to use a calculator for this as well. This would be the inverse cosine of negative 3 over root 41. This comes out to approximately 117.94 degrees. Okay, those are my direction angles for that specific vector there. Moving right along. Okay, now a quick recap on what we've been able to use the dot product for. So far it's really just been a couple of things, but we saw some interesting facts. So first of all, the dot product relates directly to the magnitude of a vector. We saw early in this section that if you take a dot product of a vector with itself, the result is the square of the magnitude of the vector you just did that with. We also showed that the dot product is very closely tied to the angle between two vectors. We used that formula to show that the cosine of an angle between two vectors is equal to their dot product divided by the product of their magnitudes. And we can use the dot product now to find angles between vectors. That's really useful. That's a really practical and useful thing to use the dot product for. However, in this class, those things, as useful as they are, sort of take a backseat to this next application. What we primarily are using the dot product for, especially in a lot of the really heavier stuff that we do in chapter 16 at the end of this course, is for the purpose of projecting one vector onto another. That's really, for our purposes, its most useful application. So we need to sort of develop this idea. First of all, what do we mean when we say that we want to project a vector onto another vector? Well, let's suppose we have these two vectors, A and B. A is this green one here, B is this blue one. When I say that I want to project one vector onto another, the more accurate term for that is an orthogonal projection. Remember, orthogonal means perpendicular. So basically, if I treat vector A as sort of the base here, I want to drop a perpendicular from this terminal point of B down onto A. Notice that their initial points coincide when I'm talking about this idea. So we take two vectors, A and B, put their initial points together, and then if I want to project B onto A, I'm dropping a perpendicular, and what I end up with is a vector that is parallel to A, coincides with A, but is not necessarily the same length, right? The length is determined by the base of this little right triangle. Now really quickly, why would you want to do this? Well, there's a number of reasons, and in fact, this is usually, in physics and engineering, this is part of a larger problem, which is decomposing a vector into a sum of two orthogonal vectors. An example is like a projectile motion problem. Suppose you're in a physics class and you're trying to look at a vector that represents projectile motion. You know, maybe this represents a cannonball being fired in a particular direction, and it forms some angle with the horizontal, right? It's pretty standard in a class like that to take the vector representing the velocity of that projectile and to decompose it into a sum of two vectors. Sometimes we call this VH for or VX, you know, the velocity in the x direction, and Vy, the velocity in the vertical direction, and the sum of these two vectors gives us the velocity vector v, right? If you haven't seen that kind of an application before, that's okay, but this is just to sort of, you know, help you tie this into something that you may have seen before. But in order to take a velocity vector like this one and decompose it, what you're really doing is you're projecting that vector onto a horizontal and a vertical vector. This might be the standard basis vector I that we're projecting onto, and the standard basis vector j that we project onto this way. So that's kind of why we like this idea of projecting vectors, is because it breaks a vector down into components that might have a more useful interpretation. For example, if I had a velocity vector that's mostly pointing upward like this, then its projection onto the horizontal is very small, and its projection onto the vertical might be very, very large. So what that implies about that projectile is that its horizontal speed is not that great, indicating it might not travel very far, but its vertical velocity is very large, so it might go very, very high, just not very far, right? That horizontal and vertical, those horizontal and vertical components of that vector end up being really useful for analysis. So I think I've motivated the projection idea enough for the time being. Let's look at how we actually do this. There's two different cases that we're going to look at here. First of all, if the angle between A and B is an acute angle, then the projection, as you can see here, is going to give me a vector that points in the same direction as A. So both the red arrow representing our projection and A point this way. If the angle between A and B is obtuse, then dropping a perpendicular from B kind of misses A. You notice A is over here, and the perpendicular is going to land behind it. So what we do in a case like that is we extend a line through A, and then we still project onto that line, but now the vector that represents our projection is pointing in the opposite direction, still parallel to A. So in either case, this vector projection is parallel to A, but it can be pointing in the same direction or the opposite direction. All right? Now, that red vector that we're talking about there is what we call the vector projection of B onto A. And if you notice the notation that I'm using, PROJ, the subscript tells me what vector I'm projecting onto, and this argument, the B here, is the vector that's being projected. Okay, so that's what the interpretation of these two values are. Notice that implies that the order is important. One of these vectors is playing a different role than the other one. But we call that a vector projection. Now, the magnitude of this vector has importance as well, and more specifically, the signed magnitude. By signed, I mean it can be positive or negative. So we call that the scalar projection, or the scalar projection of B onto A, or sometimes we call it the component of B along A, and we use this notation, COMP for component. Same subscript and argument idea there. But what is the component? Well, the component, like I said, is the magnitude of the vector, but that magnitude can be either positive or negative. If the vector projection of B onto A points in the same direction as A, then we interpret the component of this vector to be positive. It agrees with A as far as its direction is concerned, and the positive component indicates that. In the case where the vector points in the opposite direction of A, the component will be the negative magnitude of this vector. So that negative component indicates that B is sort of fighting against A. If you think of these as forces, this force is kind of pulling in an opposite direction as A, creating sort of a fight between these two, whereas here B is mostly agreeing with A. So the component would be negative in a case like this, okay? All right. So what we want to be able to do is come up with formulas for these things. Now the component is the easiest one to come up with because the component, remember, is a magnitude. We just think of it in terms of a length with the possibility of that length being interpreted as a negative number. Using the case where the angle between these two the angle between these two vectors is acute, how can we come up with the length of this vector projection right here? Well, we use the fact that this creates a right triangle and the fact that the magnitude of B would correspond to the length of the hypotenuse of that right triangle. Using a basic trigonometric argument, I could easily show that the length of this base is equal to the magnitude of B times the cosine of that angle. That's where I get that component from. Now, I want to make sure that that definition is consistent with the fact that components can come out negative. And it is. Remember, if we're up here, the angle between these two vectors would be obtuse, right? It would be somewhere between 90 and 180 degrees. But in that case, the cosine of that angle is going to be a negative number times a magnitude which is supposed to be positive. So that is going to give us a negative component where we're expecting to see one, okay? So this is how we compute the sorry, I'm losing my train of thought all of a sudden. This is how we compute the component of a vector B along A. However, this might not be the most useful way of computing this because we may not know the angle between these two vectors right away. And that's where we use what we already know to be true about the cosine of this angle. So over here, I'm going to write this. Remember, what we just showed is that the component of B along A is equal to this expression, the magnitude of B times the cosine of the angle between A and B. But the cosine of the angle between A and B, based on what we did previously with the dot product, is equal to A dot B over the product of the magnitudes of A and B. And you notice the benefit of this is that these can cancel each other. And so another way of coming up with a formula for that component is just this, A dot B over the magnitude of A. And in that case, we don't need to know the angle between the two vectors in order to find that component. I just need to be able to find their dot product and divide by the magnitude of whichever vector we're projecting onto. Okay? So that's the idea behind the component. But how then do we find the vector projection? Well, where the component here gives us the signed magnitude of that vector. Now, if you ever want to find a specific vector where you know the magnitude of that vector, one way you can do that is find a unit vector that's pointing in the direction you want it to point in, and then multiply multiply the scalar that's equal to the magnitude of the vector that you want to that unit vector. The result will be a vector with the correct magnitude. I hope that made sense. I feel like that was sort of a mouthful to say all that. Basically, the idea is this. I want to find this guy right here, the projection of B onto A. And we're supposing that I've already computed the component of B onto A. If I can find a unit vector that's pointing in the direction of A, and then multiply that unit vector by the component of B along A, it'll stretch that vector to the correct length, because multiplying a scalar to a unit vector is basically like multiplying that magnitude by 1. It doesn't change it. So coming down here, the projection of B onto A is equal to the component of B along A, remember that's the magnitude of the vector, times the unit vector in the direction of A, which we know looks like this, A divided by its magnitude. Okay? Now, Using the work that we did previously, up here we show that the component of b along A is this, magnitude of b times the cosine of the angle between them. And if I multiply this up into the numerator, I get this expression, magnitude of b times the cosine of theta over the magnitude of A. All of this here is a scalar, and it's being multiplied. I pulled this A out. It's being multiplied to the vector A. So this is a big scalar multiplication problem. Now this magnitude of b times the cosine of theta looks somewhat similar to our second definition for the dot product of the vectors A and B. What's missing is that magnitude of A up here. So if I multiply my numerator and denominator by the magnitude of A, I get this. And here we see that the magnitude of A times the magnitude of B times the cosine of the angle between them, this is the dot product of A and B. So this whole thing simplifies to A dot B over the magnitude of A squared, that whole thing is a scalar, times the vector A. And all of that work, I'm a little out of breath after all that work led to these two formulas. The component of B along A is A dot B over the magnitude of A. The projection of B onto A, we can think of in a couple of different ways. If we've already computed the component of B along A, it's just that scalar times the unit vector in the direction of A. So you can do this. Or if we use the simplified formula, it looks like this, A dot B over the magnitude of A squared times the vector A. All right, I want to do one example. Or actually, no, I'm sorry, we'll do the example in the next video. I wanted to point out something that's really, really important to note here. If I remember correctly, your book doesn't call attention to this in this section. And if I'm correct on that, I think that's a tragedy because it's going to use this result a whole lot later on. So over here, we created sort of a general argument for if you have any vector A and any vector B, and I want to project B onto A, we have this formula that does that for us. Okay, we just came up with that formula. But in applications, B is usually a vector representing some force or velocity or displacement or something like that. And A is a vector that really the only thing that we care about with A is the direction that it points. The magnitude is typically something that we pick. Now, it may not make a whole lot of sense why that's the case now, but especially in chapter 16, we're going to see that. The simplest and most natural choice then for the vector A would be a unit vector that points in the direction that we want it to point in, because unit vectors are by far the easiest types of vectors to work with in applications. So again, oftentimes B is a vector that we have no control over. It's a vector that's determined by the whatever physical context we're looking at. But A is something that we have some control over. It's going to point in a specific direction, but we have control over its magnitude oftentimes. And so for that reason, we're usually going to choose A to be a unit vector. Watch what that does to the component of that projection. If A is a unit vector, then the magnitude of A right here would equal 1, which means this formula simplifies to A dot B. Right there, A dot B. So what does that mean? Well, that means that if you're taking the dot product of A with B, then the literal interpretation of that dot product, and this is really the most important interpretation of this dot product, is that it represents a scalar projection of one vector onto another. Okay, and that really coincides with what we talked about before about the dot product. The more positive, the larger positive number a dot product is, the larger the dot product, the closer it is to, the more negative that number is, the more that the vectors are pointing in the opposite direction. Imagine here if A and B were orthogonal to each other, if B was pointing straight up. We know that the dot product of those two vectors would be 0, right? What would the projection of B onto A look like? What would the vector projection of B onto A look like? Well, if B is pointing in a way that's orthogonal to A, then dropping a perpendicular from that just takes me to a point. It takes me to the 0 vector. But that agrees with what we said before. The dot product of two orthogonal vectors should be 0. So again, moral of the story here, your book, I don't think, mentions this specific case of when A is a unit vector, but it's going to use this result a whole lot in chapter 16 in particular, and it's important to remember this. Okay, we'll go ahead and finish up this section in the next video.